Explore the outer solar system. Nearly 50 years later, they've detected a wall of fire, a superheated plasma zone 54,000 to 90,000 degrees Fahrenheit at the helipause where the Sun's influence ends. This persistent feature, measured by both probes years apart, is reshaping our understanding of the solar system's boundary and its connection to the galaxy. Watch this video to learn more about this topic. The discovery: what was found? The helipause is the invisible threshold where the Sun's solar wind, its constant stream of charged particles, fades, and the interstellar medium takes over. For decades, it was assumed this transition was relatively clean and predictable. Voyager 1 crossed this boundary in 2012, followed by Voyager 2 in 2018. Instead of a simple change in particle flow, both probes recorded a narrow zone of plasma with temperatures between 30,000 and 50,000 Kelvin, about 54,000 to 90,000 degrees Fahrenheit. It isn't a wall in any physical sense, nor is it burning. The particle density here is incredibly low, far less than even the best vacuums we create on Earth. So, heat doesn't behave the way it does in our environment. But the particles themselves are moving with tremendous energy, registering as these extreme temperatures. Scientists think this heating results from plasma compression as the solar wind collides with interstellar particles, and from magnetic reconnect ion where magnetic field lines from the Sun and the galaxy interact, releasing energy. Most importantly, this wasn't a one-off anomaly. Voyager 1's data could have been dismissed as unique to its crossing. But when Voyager 2 entered the helipause 6 years later and recorded similar conditions, it confirmed this is a real and persistent feature of our solar system's boundary. The probes also detected another unexpected phenomenon. The interstellar magnetic field beyond the helipause appears aligned with the Sun's magnetic field inside it. This was surprising. Researchers had assumed these fields would be oriented differently, reflecting separate environments. Instead, the data suggest a deeper connection between our solar system and the galaxy beyond. Scientific importance and theories. Until now, the helipause was thought to be a relatively static barrier, a shield separating the Sun's domain from interstellar space. Voyager's findings show it's anything but static. Instead, it's a dynamic, turbulent interface where solar and galactic forces meet and interact in ways we're only starting to understand. The plasma heating challenges current models of heliospheric physics. It suggests large-scale magnetic reconnect ion is occurring events where the Sun's magnetic field lines merge with the interstellar field, releasing energy and creating the extreme temperatures observed. This process likely explains the energetic particles recorded by both spacecraft. The magnetic field alignment adds another layer of complexity. Why are the fields inside and outside the helipause aligned? One possibility is that the Sun's magnetic influence stretches farther than previously thought, subtly shaping interstellar conditions near our system. Another is that the local interstellar magnetic field has an organized structure that interacts with and adapts to the Sun's field. This has implications for how cosmic rays, high-energy particles originating from distant astrophysical sources, enter our solar system. The heliosphere serves as a shield against many of these particles. If the helipause is more permeable or active than once believed, it could influence how much cosmic radiation reaches the inner solar system and potentially Earth. These insights also challenge older models of space weather on a galactic scale. Understanding how solar and interstellar forces interact at this boundary will help refine predictions of radiation levels in deep space knowledge that's critical for planning future crewed missions beyond the heliosphere. This discovery shows the solar system's edge isn't a simple boundary, but a complex, evolving zone linking our Sun to the galaxy in ways we're only starting to understand. Implications and what's next. This discovery opens new questions and priorities for space science. First, it redefines the scale and behavior of the solar system. If the helipause is more complex and active than previously believed, its size and shape need to be reconsidered. Researchers are already using Voyager's data to update models of the heliosphere and its interactions with the Milky Way. Second, it informs the design of future interstellar probes. Conditions at the boundary, extreme plasma heating, magnetic turbulence, and particle acceleration are now known factors that engineers must consider for spacecraft shielding, communications, and instrumentation. NASA's upcoming Interstellar Mapping and Acceleration Probe, IMAP, scheduled for launch soon, will follow up on Voyager's discoveries. IMAP's advanced instruments will study how the solar wind interacts with interstellar space, providing critical context for the data collected by the Voyagers and helping decode the complex physics at the helipause. This finding also has broader implications for astrophysics beyond our solar system. If our heliosphere interacts with the interstellar medium in this way, other stars' protective bubbles may behave similarly. Studying these processes offers insight into how stellar systems across the galaxy shield their planets from cosmic radiation and interact with their environments. Finally, it underscores the enduring legacy of the mission. Launched in an era before personal computers or the Internet became mainstream, these spacecraft are still pushing the boundaries of human knowledge. NASA has begun powering down some instruments to conserve energy, but key systems are expected to remain operational through at least 2026. Its discoveries raise new questions. How far does the Sun's influence reach? How does our galactic environment shape the solar system? The answers will redefine our place in the galaxy. Outro. Nearly 50 years on, the Voyagers are still rewriting space science, revealing a wall of fire at the solar system's edge and reshaping our view of the Sun's reach. What other secrets await beyond the helipause? Stay tuned. The Frontier.